All right, we're about to dive into a real cosmic crime scene. We're looking at a ghostly image from deep space that's been used for years as the ultimate proof for one of the biggest ideas in science. But what if everyone's been reading the evidence all wrong? Let's take a much closer look.
So this right here, this is the bullet cluster. And for decades, it has been the poster child, the single best piece of evidence we have for the existence of dark matter. The argument seems so simple, so direct. I mean, you can practically see the proof. For cosmologists, looking at this is like seeing the shadow of some invisible substance that makes up most of our universe. It is, for all intents and purposes, the smoking gun.
But what if that smoking gun is pointed in the completely wrong direction? What if, instead of proving dark matter exists, the bullet cluster is actually showing us a fundamental secret about gravity itself?
To figure that out, we really have to treat this like a cosmic crime scene. And like any good detective, we have to follow the evidence. The central clue is this really mysterious separation, something that just shouldn't be happening if our classic understanding of gravity is the whole story.
This image here, this composite, it basically maps out the whole scene for us. That pink stuff you see, that's these enormous clouds of superheated gas that our X-ray telescopes can pick up. Now, that's where most of the normal matter, the stuff we're made of, actually is. But the blue areas, well, that's something else entirely. That's a map of gravity itself, drawn by how it literally bends the light from galaxies far, far behind it. We call that gravitational lensing. And right there, that leads us to the heart of the puzzle. See how the blue and the pink are totally separate? The pull of gravity, the blue part, is strongest over here with the galaxies. But most of the ordinary matter, all that pink gas, is stuck way back in the middle. So why is gravity's ghost detached from its own body?
Well, there is, of course, a very popular explanation for this mystery. You might even call it the prime suspect, one that has dominated how we think about the cosmos for the better part of a century.
The dark matter hypothesis paints a pretty clear picture. The story goes like this. Two huge clusters, each with stars, gas, and a massive halo of invisible dark matter, came along and flew right through each other. Now, the dark matter and the stars themselves, they're collisionless. I mean, they're so spread out they just kind of ghost right past each other. But those huge gas clouds? No way. They couldn't do that. They slammed into each other like two giant waves in the ocean, creating that super hot pink region you see in the middle. So that blue gravity map, according to this theory, isn't tracking the gas at all. It's tracking the invisible dark matter that just sailed right on through with the galaxies. Case closed, right?
Well, maybe not. That neat and tidy explanation, it isn't the only one out there. There's a whole different way of looking at this. A theory that suggests we don't need a new kind of matter at all. We just need a new rule book for gravity itself. It's called dynamic vacuum field theory, or DVFT for short. And it proposes something pretty radical. It says that gravity and lensing don't just come from mass. Instead, they arise from the coherence of the vacuum field. Okay, think of the fabric of space-time like the surface of a pond. It can be perfectly smooth and orderly, or it can be choppy and chaotic. This theory says gravity is strongest where that pond is the most orderly. And this analogy really gets to the heart of it. That hot, messy, collisional gas, it's like throwing a bunch of rocks into the pond. It creates chaotic noise in the vacuum, scrambling up any order. But the galaxies, they're organized, and they pass right through without colliding. They imprint these stable, coherent patterns, kind of like standing waves. So DVFT predicts that gravity and the lensing it causes is going to track those stable patterns and mostly ignore the chaotic noise.
So here's the bottom line. It's all about this big difference. On one side, you've got the hot, turbulent gas from the collision. Its violent nature just destroys the vacuum's coherence. It's messy. On the other side, you have the galaxies, which are these beautiful, collisionless systems. They sail right through the mess, preserving their organized structure and with it, the vacuum's coherence. This theory predicts that even though that gas has a ton of mass, its contribution to gravity should actually be pretty weak.
Okay, that's a really fascinating idea, right? But can you actually test it? Can we measure this effect? Well, the folks behind this theory say yes, we absolutely can. And they say the proof is hiding in plain sight, right inside the original data. And the process, believe it or not, is surprisingly simple. And it just uses data from a famous 2006 study. First, you just measure how much normal matter, so gas plus stars, is at the center of the gas cloud compared to the center of the galaxy cluster. Then you do the exact same thing for the gravitational lensing signal. The difference between those two ratios gives you what DVFT calls the collisional suppression factor. So let's start with the matter. The data shows there is 1.8 times more normal baryonic matter located at the peak of that hot gas cloud than there is at the peak where the galaxies are. So you'd think, if gravity only cares about mass, the cosmic scales should be tipping heavily toward the gas cloud. It should be the center of gravity here, no question. But it's not even close. When we actually measure the lensing signal, we find the exact opposite. The gravitational signal at the gas peak is only 10% of the signal at the galaxy peak. It's 10 times weaker, even though there's almost twice as much stuff there. And this is the million-dollar question, isn't it? If there's more matter in the gas, why is its gravity signal so much weaker? I mean, if gravity is only about mass, this makes zero sense unless you add a whole bunch of invisible stuff. But if gravity is about coherence, well, this is exactly what you might expect to see.
And now for the final calculation. When we take that lensing ratio, 0.10, and we divide it by the mass ratio, 1.80, we get this number, 0.06. And this is what the theory calls the collisional suppression factor.
So what on earth does that mean? It means that all that hot, messy gas is only contributing about 6% of the gravity you would expect from its mass. Its gravitational potential has been suppressed by a staggering 94%, which is exactly what DVFT would predict for a system that destroys the vacuum's coherence.
So where does that leave us? We have two completely different explanations for the same cosmic crime scene. Let's put them side by side for one final showdown. All right, on one hand, you have the standard dark matter model. It explains the offset perfectly, but to do it, you have to invent a brand new particle that makes up 85% of all matter in the universe. Other alternative gravity theories like MOND really struggle here. They still tie gravity to all normal matter, so they can't explain why it's separated without also adding some invisible stuff. But then there's DVFT. It also explains the offset, but not with new matter. It does it with a new mechanism, a measurable suppression of gravity that's tied to the physical state of the matter itself.
And you know what? The very latest, sharpest data from the James Webb Space Telescope just makes this picture even clearer. It confirms that separation with even higher confidence. And it shows that the gravity map follows the faint light from scattered stars, what we call intracluster light, with incredible precision. Now that's a really powerful observation. Remember DVFT's whole idea. Gravity tracks order, not chaos. This faint starlight comes from stars that pass through without colliding. It's the perfect tracer for that orderly vacuum. And that hot gas? It's the perfect tracer for the chaotic noise.
So, the bullet cluster. For so long, it's been the poster child for dark matter. But maybe, just maybe, it's been trying to tell us something much more profound. That gravity is more complex than we ever imagined. And it forces us to ask a really big question. If gravity's strength can depend on the state of matter, not just how much of it there is, what does that mean for everything else we think we know about the universe?